All right, here we go with a discussion on ionic equilibria and specifically what we call solubility product constant or Ksp. So you probably remember back in Gen Chem 1 where we talked about the solubility rules. Well, it turns out that all ionic compounds dissolve in water to some degree, but the ones that have such low solubilities were the ones that we put in that category of insoluble. But if it happens to be something that could be dangerous, that solubility can prove to be quite problematic. So we can um, we can apply the equilibrium in the same way that we've applied it before, and we'll use the constant to measure how much is in there. So we use something called a KSP, or a solubility product constant. Okay, and the generalized form of this is seen in this center here, where it says, look, if you have some kind of metal with an anion, M sub n, X sub m, and it is primarily insoluble, in other words, it's a solid, then we can measure using the KSP what that solubility is, and we'll measure that solubility in terms of the amount of the metal that goes into solution. So when you solve that KSP, you take the metal, and that is raised to the n power, and you take the anion, and that is raised to the m power. So let's think about something like PbCl2. Here it is. It shouldn't be at all surprising that that becomes KSP is equal to Pb2 plus Cl minus squared. This goes away because of the S behind it, right? And so we're only concerned in the KSP with things that have measurable concentration. Now, there's there are going to be some varying degrees of difficulty here, if you will, right? The dissociation for AgCl is pretty simple. It goes from AgCl as a solid to Ag plus and Cl minus. So that Ksp turns out to be concentration of Ag plus ion times the concentration of the Cl minus ion. Okay, so now what we've got is we've got all of these compounds that have some amount of solubility, right? I mean, again, if you look through these, you'd say, oh gosh, those were all in the table, right? Where we're in the solubility rules, right? When we first look through those, and now it turns out that they're slightly soluble, or what we would describe as sparingly soluble salts. And you can tell by these, right? So the KSP is moving in the direction of the ions, right? The dissolution. And all these are pretty small, right? I mean, 10 to the minus fifth is the largest one we've got here. You see copper sulfide here, 10 to the minus 36. That's highly insoluble. Things like lead sulfide, highly insoluble. All right. So what do? We use the ice table, right? Here's the ice table. You can use X or you can use S here. But what happens is as we move in this direction, right, we get some Ag plus and we get the same amount of Cl minus. And so the change is S and the change is S, and they're both plus S, right? And that plus S turns into S at equilibrium. And so, for instance, you would have the KSP equaling S squared, right? And recognize that S is the concentration of each of those. Solving this, you get again S squared. Take the square root of the KSP, and boom, you've got S, right? So now we've got the way we would report this is the solubility is 1.33 times 10 to the minus fifth, which equals the Ag plus concentration, right? Because in general, the anions are of no consequence at all, and so we're worried about the metals. Can take that back to a concentration, and that concentration turns out to be 0.00191 grams of AgCl per liter of solution or liter of water. So normally what we're solving for, right, is the solubility of the solute that's going to dissolve in a given amount of solution. And it's going to be at a particular temperature. We know that because the Ks are always at a specific temperature. The molar solubility is the number of moles that will dissolve in a liter of solution. And so when we say that we're solving the equilibrium, the Ksp, and we're simply doing it for the concentrations, we are looking for a molar solubility. So this is just a rearrangement of that equation before, right? So taking the whatever the root is here, right, of the two exponents, dividing through ks, dividing ksp by the two n and m, and taking again that root. Okay, so let's look at some of these, right? Calculate the molar solubility of PbCl2 in pure water at 25 degrees C. So first of all, we establish the ice table, recognizing that there's a 2 here, right? And so it's going to be S and 2S, right? So that's going to be the equilibrium condition. Then plug that in, and we get the KSP expression up here, right? So S times 2S squared, right? And so that equals down here 4S cubed. Divide through by 4, take the cube root, and you come up with the solubility, right? And now that solubility is actually already in terms of PB. So a quick practice, the KSP of PbR2, if its molar solubility in water is 1.05 times 10 to the minus 2, well, we know that PbBr2 goes to Pb2 plus and 2Br minus, right? And so this is going to be S, 2S, it's going to be S to the first times 2S squared equals the KSP, right? And this is the solubility, right, at 25 degrees C, and so that's S, boom, put one there, and solve, and we'll get the KSP. We just did it quickly on that previous one, but here it is using the extended version with the ice table, and you get to these equilibrium conditions and plug them. Here's the KSP, right? Here it is plugged in, here it is solved. So we get a KSP of 4.63 times 10 to the minus. So this is kind of important because when we start to compare different compounds, we have to take into account the stoichiometry, right? You looked at AgCl and it was pretty simple. It's the square root. Well, that's different than taking the cube root of something, and so it matters. The stoichiometry matters, and so what you have to compare is not just KSPs, but the actual solubility of the metal itself. We also have to be concerned about what the other ion is in this process, right? Because there can be an instance where we have a common ion. So if you had NaCl, right, you're in salt water, let's say, or even KCl, that changes that equilibrium, okay? And so the amount of Pb2 plus that is dissolved is different than if this were in just pure water. So here's what the common ion effect does, right? It shifts the equilibrium to the left. Because if there's a common source on the right-hand side, that means that there's product. That product then means you shift to the left. So how do we deal with this? Well, we deal with it using the ice table, right? It doesn't add too much to it, except that now what you have is you have a starting amount of F minus. And so if you have a starting amount of F minus, then what happens? Your equilibrium term has to include that. So again, we write out a KSP, right? We plug in our equilibrium conditions, And then because the Ksp is pretty small, right, we then can go ahead and drop the s, right? It's similar to dropping the x, right? Meaning that it's not going to make any difference in the value of zero point 0.1 squared, right? By doing that, it simplifies things. Plug it all in, right? The Ksp was 1.46 times 10 to the minus 10th. This is to the minus 1. That means we can drop the x. So let's look at a little practice problem here, right? Determine the concentration of Ag plus ions in seawater that has Cl minus of 0.55 molar. And again, you're given the Ksp, this Ksp of 1.77 times 10 to the minus 10th. Obviously, we're going to be able to drop the x. So here's the ice table. At equilibrium, Ag plus is S, Cl minus concentration 0.55 plus S. Now it's a matter of plugging it in, right? Here's the expression. Here it is plugged in, right? Here it is solved, right? And you get 3.2 times 10 to the minus 10th. There are a lot of ways that there are a lot of ways that pH can affect solubility, right? For slightly soluble hydroxides, the higher the pH, the lower the solubility, right? The lower the pH, on the other hand, the higher the solubility, right? For insoluble ionic compounds with weak acids, right, the lower the pH, the higher the solubility. So you have to consider what's attached, and then you also have to consider how the pH is going to affect it. So one of the values of this Ksp is to determine precipitation. So when the ions in solution exceed the solubility of the compound, it will precipitate out. So we can start by saying, okay, if we compare a Q, right? You remember what we did? We plugged in quantities and said, where are we in terms of the equilibrium? If Q is equal to K, well, there's no precipitation because the solution is just saturated. Q is smaller than K, the solution is unsaturated, right? If Q is actually greater than K, though, that means it's above the saturation point and there's something that will precipitate out. So a Q greater than Ksp might not precipitate unless it's disturbed. And until you get into some other labs, you're not gonna notice this. But a lot of times, you actually have to disturb a supersaturated solution to actually get it to precipitate out. So here we've got an example of sodium dichromate, and you're adding in the sodium dichromate into silver nitrate. Now, if you go back to the solubility rules, you know that all sodium compounds are soluble and all nitrates are soluble. So these these top two here, right, this one and this one, both soluble, but then this is not. Okay, so as you add the Na2CrO4, the Q is getting greater than the Ksp. And here on this side is this example of supersaturation, right? You don't have anything in solution here, but if you drop a crystal in, you seed this, all of a sudden you'll see all of this precipitating out. So a way we can take advantage of this precipitation is we can do what we call selective precipitation. So we can take a solution that might contain different cations, and if we know what they are insoluble with, we'll go back to the solubility rules, we know that they're sparingly soluble, but we could separate them by adding that anion that is common to all of the cations, and they should separate out if their KSPs are different enough. So here's an example of this. So the question is, will a precipitate form when we mix lead nitrate with sodium bromide if the concentrations after the mixing are 0.0150 and 0.0350? So we solve the equation to say here's the solid PbBr2. Here is then its resulting um, equilibrium. The Ksp is given here. And if we solve for these conditions and compare this 1.84 times 10 to the minus 7 to 4.67 times 10 to the minus 6, the Q is actually less than the Ksp, and so this will not precipitate. So a little practice question, right? Will a precipitate form when we mix calcium nitrate with sodium hydroxide if the concentrations after mixing are 0.0175 and the Ksp is given? So now you know what the solubility looks like. You know that the CaOH2 is the solid in solution, and so you'd write the Ksp this way, and it would go to Ca2 plus and 2OH minus, right? You're going to plug into the concentrations and say the Ksp is equal to um, 0.175 and 2 times 0.175 squared. Solve for that. That gives you actually a Q, right? And then compare it to the Ksp. And here's that solution. So again, plugged in 0.175. Should have been 2 times 0.175 or 0.0175 and gotten this Q of 5.36 times 10 to the minus 6. Sorry, a correction here, right? This is correct because they actually said both of the concentrations are 0.0175. Okay, so they identified both of those concentrations. We didn't have to take that into account in any kind of ICE table. So here's a question of what's the minimum OH minus concentration to just begin to precipitate Mg2 plus, and the concentration is given in that. And so what we're going to do is we're going to say, okay, if you are at the Ksp, you are just going to start the precipitation. Anything more than that, right? And so you've got the Ksp of 2.06 times 10 to the minus 13. You plug in this 0.059 and then solve for the OH minus concentration, and that's the concentration required to just begin precipitation. So remember back to that pH discussion we had. As you increase the OH minus, right, you shift the equilibrium to the left and you begin to precipitate the MgOH2. On the other hand, you could decrease, right, the amount of OH minus by adding H3O plus, and that would result in shifting to the right. So this is that pH adjustment that we talked about earlier. So let's say you wanted to go at this from a different direction and say you've got an amount of NaOH. So you've got a concentration of NaOH. What concentration of calcium nitrate would you put in, right, to start that precipitation? And so again, what we're going to do is we're going to look at this and we're going to say, okay, when we match that, then we can start the precipitation. We also then know that CaOH2 is going to go to, is going to go to Ca2 plus 2OH minus. Right, and now we know what this concentration is over here. And so we can plug it into the Q and say, okay, where does this match the Ksp? And then we can say, well, it's the concentration of Ca2 plus, right, times this concentration of 0.0175 molar squared, right, and solve for the Ca2 plus. So here's that solution, right? We would get down to the bottom here and we would need 0.0153 molar Ca2 plus to start that precipitation.